Hello everyone and welcome to a new Lifehack. This is Patrick from NUMECA Engineer Bureau, and today we will be covering a lot of aspects of the post-processing in Fidelity. Specifically, we will be addressing all the main features that you need to post-process your simulation, and we will also try to highlight a lot of new features which have been released with the last release 23.1. As a case, we are using this centrifugal compressor, and we will be covering all the important topics from creating contour plots, how to manage your views, how you can create integrals. Be sure to stay tuned and let's get started. So as soon as you enter the results analysis context in Fidelity, you will start with a predefined view as you see it right here. That is, if you are using the turbo template, you end up with this ZR view on the upper left. You will have a blade-to-blade view on the bottom left and a 3D view on the right side here. However, and this is the first point I would like to stress, you do not have to maintain this view. So you are completely free to just organize your view just as you see fit. So for instance, I can just split this window, create another meridional view, and maybe create another one. For instance, if I would like to compare three simulations. So let me just fit the view here. Also, maybe I would like to synchronize the view of all those three. You can do that by simply right-clicking the view that you want to take as the template, and then you say right-click, bind views camera, and then just click on the next view that you want to synchronize, and now as you can see, they are in sync. Also, you can add this third view here. All you do is you again select bind views camera. However, and this is also highlighted here by this short explanation, now you have to keep the control button pressed in order to maintain the binding to this view as well. And now as you can see, all three views are in sync. All right, so let's continue with the contour plot. Let me just change the view for this. So I will be using this meridional view to create first a contour plot, followed by isolines and some vectors. However, the principle can be applied to any other view, so the 3D view or the blade-to-blade view, the principle remains the same. So what I'm going to do here is I would like to create a contour plot of the static pressure here for the entire machine. Therefore, I will simply select all the domains, which are 5 in total, so 3 rows and the ZR effects. And now I can create on this button right here to create the contour plot. Down here, I will simply click apply. This is probably going to take a couple of seconds. Let's just wait for that. Next, we will be addressing the color bar. So as you can see, our plot is completed. I will now do some modifications regarding range, colors, and the plot itself. First of all, I right-click the color bar and say change orientation. Let's just do that. Let me modify this view a little bit. So the first aspect I would like to change is to set the contour plot from smooth to stripes. You can do that simply here. Next, I can increase the number of contours and the decimal points for the pressure. I don't think we are going to need those. Next, I would like to change the range a little. Therefore, I select set user range, and then let's see, for this case, I will set the limits from 3 bars to let's say 1.3 megapascal. And now I have a nice contour plot. Next, I would like to overlay this plot with isolines, matching the contours that I just created. Therefore, I again just select the domains that I'm interested in. I go to create isolines and enter the same limits I just applied to the color bar. That is 300 kilopascals and 1,300 kilopascals, if I remember correctly. Yes, and now as you can see, the isolines match the contours of my contour plot. I can rename those and say isolines of static pressure, and I think I would also like to reduce the line width. Yeah, that looks better. The last probe that I would like to add is a vector field, and in this area there have been some additional modifications with the new release of Fidelity 23.1. I will highlight those in a minute, so let me just again select the main channel. In this case, I will say create vector field for the velocity. And what has actually changed is that now you are not limited to plot one vector for each mesh vertex. You can now do a random resampling and specify a number of points per square meter, which very often can be more appropriate. So I will just select apply, wait a couple of seconds. So as you can see, now we have our vectors, maybe a little bit too big. I will just add a couple of vectors for the ZR effect. I'm doing those separately because here indeed I would like to have a vector on each mesh vertex and say apply. So as you can see, we still have some fine tuning to do. So what I'm going to do first is, so I'm going to call this vector field main. I am going to decrease the size of the vectors. So in our case, let me take a look at my cheat sheet. So we have 0.2 for the main flow path. So that looks good enough for me. And for, let's see, vectors leakage, I will simply reduce the size of the vectors here to 0.01. So now I can zoom in, and as you can see, here we have our vectors. We can see, let's see if I have the correct. Yeah, I do. So here we see our vertices. We can see that the flow is actually going back from the second stage to the first stage, which is simply due to the higher pressure, as we can see here. In the next part, we will be creating a cutting plane on a constant span, followed by a contour plot, and we will be intersecting the cutting plane with the blade to create a Cartesian plot of the variable that we used for the cutting plane. And I think this sounds more complicated than it is. So first of all, let's create a cutting plane. In our case, I will be choosing a blade-to-blade plane on, let's say, 80% span. As you can see, it already has been created. Maybe let me remove the shroud for you. So here on the assembly level, right-click, you can edit several viewing options for your turbo machinery configuration. So here I can simply say hide the shroud, and maybe let's also hide the interfaces, and now we have a clear view on our cutting plane. Next, let me plot, let's say, for instance, the static pressure on this plane. We already went through that, how to do that. And now I would like to intersect the blade with the cutting plane and plot the value in a Cartesian chart. In order to do that, I will split this view up here and create a post-processing chart plot. Next, I can simply select my cutting plane, and in our case, I would like to intersect it with the main blade of the first impeller. So I select those, and now here I have this option where I can say add curve from cutting plane intersection. So let me just press that. And I don't know if you have seen it, but now a new curve right here is created. I can enter the chart, select the computation that I would like to choose to show the results. And now I can select, for instance, let me just apply the filter here. Let's take the meridional coordinate for this, and maybe the static pressure for the y-axis. Let me highlight, or let me change the range. And now what we see here is the static pressure plotted over the meridional coordinate along the intersection of the main blade and the cutting plane. Maybe one last point that I would like to show is if you right-click the assembly, you are also able to activate the repetition. So let me just do that for you. And now we get a full 360-degree representation of our geometry. However, that does not include a repetition or reconstruction of the flow solution. That is something that you have to do manually. In our case, for the cutting plane, I can simply select the color contour, which is the static pressure in our case. I can go to reconstruction and, for instance, click compute all passages and say apply. This will take 1 or 2 minutes. Oh, actually not, it's a lot faster. And now we have a full representation also of our flow field and not just the geometry. So we are approaching the end of our life hack. So let's do the integral. For instance, if I would like to have the averaged total pressure at the inlet, you can just select the boundary. It can also be a cutting plane. And then move to this button right here where it says create integral. And then you have different options here that you have at your disposal. So let's say, for instance, what I'm going to need is an absolute weighted mass averaged value. And if you're not quite sure about the definition of the integral, you can just hover over this information button and it will give you the definition. In my case, this is already complete, so I would like to use the absolute total pressure as the weighting and say apply, exit, and now I have a new integral down here which gives me my absolute total pressure of 325,000, which is good because that's the boundary condition that I set. I can also rename this. Let's say absolute total pressure at the inlet. And this becomes actually important because every integral that you create here can be monitored during your simulation. And in order to know which is which, it might be important to assign a proper name here. That's all from my side. I think we covered quite a lot, so be sure to shoot us an email if you have any questions, and have fun trying it out yourself.